Hey guys, so today we are going to talk about multiplying complex numbers. In the last video, we talked through adding and subtracting. We have some videos on how to simplify complex numbers, whether that's simplifying a power of I or simplifying a radical into an imaginary number. And so today we're going to use those powers of I and what we already know about multiplying to be able to multiply complex numbers. So a couple of reminders in terms of the pattern that I follows. So you already have this in your notes if you watched the other videos, but we all know that the square root of -1 is by definition equal to I. That is an identity. That is always the case. That doesn't change. So we know that the square root of -1 is I. That I squared then can be simplified to be -1, I to the third as -I, and I to the fourth as 1. So we're really going to focus on this I squared equal to -1 portion for today, because that's what we use when we are multiplying complex numbers and end up with an I squared in the answer. So as we're multiplying complex numbers, just a couple of notes. We have to make sure we completely distribute. Now, this is not something just with multiplying complex numbers, but multiplying complex numbers uses the same multiplication rules as when we are multiplying any other set of mathematical terms. So we have to make sure we do fully distribute when we're doing this. When multiplying by binomials, one method we can use is the FOIL method. Remember, FOIL isn't the only way to do it. It's just a method we use to make sure that we are fully distributing one complex number or one binomial to another binomial. And then finally, this is something different and new. When we're multiplying complex numbers, we must end with a complex number, a plus or minus bi. So in other words, we need to make sure we're fully and completely simplifying everything we can so that we have one real component and one imaginary component. Even if one of those components, one of those pieces multiplies and then cancels out, we still want to make sure we only have one of each. So let's take a look at an example. So the first thing we want to make sure we do is fully distribute our complex numbers. Then if we have an I squared from multiplying, we want to simplify because we know that I squared equals -1. So we can substitute -1 in its place, combine like terms if necessary to a complex number, and then make sure we have written it in the form a plus or minus bi, so where we are making sure we are real upfront with our math. So let's multiply 5i times 3 minus 2i. So as we're distributing here, I'll distribute the 5i to the 3 and the 5i to the -2i to give me 15i minus 10i squared. Now, if these were x's, I would stop here and be like, oh, cool, I'm done. But they're not. We know what I equals. I has a value, and as does I squared. I squared has a value of -1. So this is where the second step comes in. We're going to simplify or substitute I squared to be -1. Since we know that that's what it equals. And so then I have -10 times -1, which would change to a +10. And then finally, no like terms to combine because I have one real piece, one imaginary piece. They just have to be in the right order. My real part has to come first. So 10 plus 15i would be my final answer. Let's take a look at another example. Here I have 2 plus 5i times 3 minus 7i. So this is a case where I have a binomial times a binomial. So I want to make sure that I do fully distribute every term in the first set of parentheses multiplied by every term in the second set of parentheses. So one method we've used for this is the FOIL method, first, outer, inner, last. So multiplying the 2 times the 3, the 2 times the -7i, 5i times 3, and 5i times -7i to get 6 minus 14i plus 15i minus 35i squared. And then here, just like before, when I have that I squared, I know that I squared by definition equals -1. So I'm going to simplify that down or substitute that -1 in place of the I squared, which makes that -35 a positive 35. Because the negative times the negative gives me multiplies to be a positive. And so now I can combine my real portions and I combine my imaginary portions to get 41 plus I. So let's just take some notes on the definition of a complex conjugate. So complex conjugates are complex numbers that, when multiplied, cancel out the imaginary part. They cancel out the imaginary number. They're not exact opposites. You can't really say that, but they are in some ways opposites of each other, which you will see. So a complex conjugate takes the form A plus BI and A minus BI, where the real part is the same and the imaginary part is opposite signs. So for example, 3 minus 5i and 3 plus 5i are complex conjugates. So this is a case, though, where when we multiply, if we were to multiply those together, we would expect to, because they're complex conjugates, not have an imaginary part in our final answer. So let's take a look at these two complex conjugates. Multiplying 7 minus 3i times 7 plus 3i. Again, doing our full distribution, FOIL. You could use a box method. You could use just a general distribution method. Whichever method you choose, you should end up with 49 plus 21i minus 21i minus 9i squared. So here again, there's a couple of directions you can go with this, a couple of ways you could start or continue this from here. I always like to just get my I squared out of the way right away so that I don't forget to do that later. So I know that I squared is -1, which means I have 49 plus 21i minus 21i plus 9. And then notice here when I actually combine that 21i and the minus 21i, those will cancel. And so the 49 plus the 9 would give me just 58. So this is an example of when multiplying complex conjugates, you end up with only a real answer.